put it up on YouTube. Okay, so let's start. Now, before I start, let me give you a background where we are, so that we have a idea of. Let me change to another page. Okay, let's summarize what we have done so far. Now, if I were to summarize our data structure journey so far, we started with lists. Okay, we started working with lists first, that is linked list. We did all kinds of lists. Then we did trees, because we said this is faster. Then in trees we did binary trees. Then we did BSTs, and we also did avial trees. For trees which were BST but not balanced, we did avial trees also. So this is what we did with trees. Then under trees itself, we did things which look like trees but are not trees. We did min heap. I think we did min heap or max heap, it doesn't matter which one of them is okay. We also saw how min heap can be used in C++. Okay, we did, no? We saw how min heap could be used in C++, and which is called priority queue or something. And we saw how we could have our own comparator logic for the min heap. So this is where we are. So we have seen that tree as a very good data structure, list as a very good data structure. So today we are going to see another data structure which is called a hashing or hash data structure. Okay, there is a little advantage of hashing. Of course, it all depends on the quality of the hash function, and we are going to discuss that today. So what role does hashing play? Now, if you see any of these mechanisms, okay, the best case performance for, let's say, retrieval, for retrieving any data, was if you say min heap, it was O of 1, but if you take any of the others, O of n, O of log n. Okay, this was the best we could do with avial tree or with BST. So with BST it could even get worse, because it could become a degenerate BST and it would become O of n. Okay, we could improve it by balancing the tree to O of log n, and if you used min heap, it would be O of 1. But in min heap also, if you had to store data, okay, or any of these things, if you had to store data, the minimum time required would be O of log of n. That is, if you wanted to update any of the data, you would still need log of n, right? So that was the problem. Okay. Now hashing tries to score something like this. Its addition is O1 unit of time, and its retrieval is also O1 units of time. So to add new data, you need O1 units of time, one computation, and to retrieve data also you need one computation, that is O1 unit of time. One computation is 1 unit of time, right? Now you will say, then why is hashing not used in place of all of this? Well, hashing, obviously, there are some good things, there are obviously some bad things. Okay, so it is not without its own defects, but when hashing is implemented successfully, and hashing is a good strategy, it does give O of 1 performance for retrieval also, and for insertion or updation also. Okay, so or deletion, I think, is an updation. So that's the promise of hashing. So that is what we are going to look at in hashing. Okay, now what do you mean by the word hashing? Hashing is very common. All the cryptocurrencies are based on hashing. So hashing is a very important idea and a concept. So what does hashing mean? So hashing, I think, comes from the word hashish. Okay. Now, does anyone know what hashish means? Let's look at the chat. Are you're not sharing the screen? Okay, we'll share the screen. Nothing was lost. Anyway, it was more talk. Be careful.
Sir, recording?
Recording is started. Okay, go to the. No, that is fine. Just go to the chat window. Back arrow. Here, back arrow. Yeah. So, yeah, we have started. Yeah, we have started to share the screen. We didn't do it, but we didn't miss anything. Okay, now the question for you is, do you know the meaning of the word hashish? That is what I was asking. Hashing comes from the word hashish. Move this. Can you? Just move it. A sec. No, not that. This window. Hold it inside. Left. Yeah. Okay. So, yeah. Now I just asked this question. Do you know what is the meaning of the word hashish? Hashing comes from hashish. I'm just curious. Okay, good. It's a drug. That's right. Okay. So, okay. So I think that is a good starting point for today's discussion. So hashing comes from hashish. Hashish is some kind of a opiate, some kind of a drug. No, yes. Okay, sorry. It's some kind of a drug. So under the influence of drug, what do? You have random behavior, right? It's not predictable behavior. When you have drugs, you start behaving in random. So hashing comes from this hashish, which is basically randomizing your behavior. Now a lot of people don't like random behavior, but believe me, and hashing is a proof that randomization is a good thing to happen. And very often in computer science, we get the benefit of randomization. So let me now go ahead and describe what hashing is and how does it work. So let's say, before this, I hope you are understanding the whole of B trees or BSTs or AVL. You know why they were created? They were used to create indexes. What is stored in a BST is basically indexes, which means that when you have a node, then in a node, of course, you store data, but you really don't store data. You store basically the data which is to be found, and against that you store an page number or an address. Okay, the physical address of where you will find the record. Okay, let me explain what it means. It's worth explaining at this stage. So, okay, let me talk about this. So let's say you have lots of employee data. Okay, you have employee data. So you have records and maybe trillions of records of employee data. In memory or on hard disk, let's not worry about it, because now that border is started to change as to narrow. So this is employee data. Okay, records and records of employee data. Now on the employee data, if you have to look for a particular record, if you want to look for employee number 101, now you have to practically and sequentially, if you didn't have an indexing mechanism, because the employees are, let's say, randomly done, there is no particular sequentiality in the way employee records are there, because employees add and leave on demand. So they are not in any particular order, and you are looking for employee 101. So you have to conceptually go through all the employee data blocks, that is maybe trillions of records. So obviously that is not acceptable. So what do? You store and you create an index, okay? And the index basically gives so what is there in the index? The employee number 101 and where it is found, that is the physical address. The physical address is stored along with the index, and the index is what gets stored in either a BST or an AVL tree or in a priority queue or wherever. So it's the indexes which we use to store in our trees. So our trees store indexes. So when I'm looking for a particular employee 101, let's say, I start with employee 1 and then I decide that it is more than 1, so I go to the right. Maybe the right is employee 100 and it's still more, so I go to the right, and somewhere here I find employee 101 in my BST, and there I find the physical address which will point me to this address. So I'll go through this index, locate the address, and then go to the physical record and pick up the physical record. This is how and that's why this data structures are very important, and that's why we are spending a semester learning these data structures, whether it is balanced or a BST or not a BST or whatever. These data structures are the quicker ones because they lead me to data. If they are well organized, they lead me to the data in log n units of time. Actually not log n. Log n you will find this. After that you will have one more access to pick up this record, okay, to pick up this block, and in that block you will find your record. So this will point to the block address and the record address. So you'll have to read the entire block in memory and then sequentially read the block to find the physical record. But that's a lot faster than going through all of them. So that's essentially why this data structure course is so important, because it enables you to optimize this. If you optimize this, basically you are able to get to your data faster. So all of the indexing strategies are based on these data structures, these principles, and this is how we store data. The other data structure you would have is dictionary or something, which would again come down to the same thing. Now, hashing kind of turns this thing completely around and says we will do something like this. So we have, again, in a similar analogy, how would it work? I am looking for employee 101, okay? So if the data was stored in a BST, you just saw what happened, that I would search the BST, find the index that is this 101 would be in the BST, and against that I would have the physical address. In that same record where I find 101, I would have the physical address with which I would go and retrieve the data. So, so to put it very simply, I would need 1 plus log n number of accesses, n being the size of the index tree, okay, these many accesses to get to the record, okay, if I am looking for 101, because I have to search through the BST. On the contrary, this is what a BST or a balanced BST would do for you, okay, it would give you 1. Why is this 1 there? This is for the, once I have found the physical address, I still need to have one more access to bring it in main memory and then check. That's why this extra access. But if I had the data using hashing, something very magical would happen. What would you do? You would take this 101 and pass it into a function 101. Okay, the function would take 101 as an address and it would generate a physical address straight away. Okay, so this function, its job is to take the index that you are looking for and output the physical address where you would find 101. Now, this is just one computation and the total time taken would be 1, because I have already got the physical address. To access the physical address, it is this one. But I don't even need log n. I just have to pass 101 to a function. It does some computation, which we always say is 1 unit of time, because it's not going from here to anywhere. It's just taking 101, doing something on it, and generating an address. So this is just going to take 1 unit of time. And then you have one physical address, which is to access the data, like you had this one here also. So this whole of log n, which you would get with a BST, would become just 1 unit of time, and it would be output of a function which we traditionally called a hashing function which would hash it to a particular physical address, and at that physical address this record will be kept. So 101, you can, in just 2 units of time you can reach that record, whereas here you would need 1 plus, if there were a billion records, this would be 30, you would need 31 units of time. And here, if you had still billion records, you would need just 2 units of time. So this is the promise of hashing. Of course, this is an idealistic promise. This depends on the fact that your hashing function is just perfect or near perfect, where it can generate addresses, but in real life it doesn't happen so. But this is what it is supposed to happen, and it is supposed to give you a best performance of 2 units of time. Here even the best performance, will be higher. Here the worst performance will also not be too different from 2 units of time, though we know it will be worse. The question is how much worse. So I am just giving you an analogy, of how hashing works. So it takes the employee number, gives it to a hash function, it directly generates a physical address, and that physical address can then be used. No going through a tree, no nothing, just this computation, and you get the physical address. Isn't it something magical? So this magical guy here is the hashing function. It's not magical. It is actually has a lot of flaws in it. And part of understanding hashing is to understand those flaws and understand how this all happens. Okay. So if the basic premise of hashing is clear, then we can proceed and understand how it's going. Okay. So now, are you clear about the basic idea of hashing without getting into how hashing happens, what you need to do about hashing and all that? So hashing is, instead of log n units of time, you just give your 101, which is your key value, to a function. It computes that output and gives you the physical address. That is all it does. So that is the big promise of hashing. Okay. If it works well, it's a very strong weapon. But if it doesn't, then you have a problem. Okay. So as far as your course is concerned, I think you just need to understand hashing. You don't need to implement hashing, but I'm sure when you do more, you'll learn to actually implement hashing. So with this said, I'm going to walk you through a PPT which we have. We just picked it up from the net, and as I go through the PPT, I'll explain each step in hashing. So you have to understand some fundamental things in hashing, and that's it. We are ready to move on. So we are at 11:50, and I think we will do this. I think we should finish this by 12:20 or something, and then we will do Flask for a bit and see how it works. Okay. So let's move on to the next slide. A hash table or a hash map. Okay. Those of you who will get familiar with Java or C++ will know what is a map. Map is called by various names. It's called a cache. It's called, it's called dictionary. All of these are based on hashing principle. Okay. That is, given a key, use a function to find the physical address in the data. You'll soon see how it works. Next. Okay. So these are your keys. Okay. And these are your actual data which is there. And these are the generation of the indices. Okay. So if you see this, if you were to do this, so here, this is your key, and you have to reach this address. Okay. Now you have to search an index. You have to generate an index, and at that index, this value will be there. Here, indices means the physical addresses at which the record will be available. So now you can search through something. These indexes can be kept in a BST, but when you're doing hashing, no, you don't have a BST or anything. What do? You take John Smith. So imagine you're looking for John Smith. So you give this John Smith as a parameter to a function which we call the hash function. You give John Smith as a parameter, and when you call it with John Smith as a parameter, it generates an index, which in this case is 873 automatically. And then at 873 index, you have this physical record for John Smith. There may be other data about John Smith which may be recorded here. So the same thing happens with Lisa Smith. So you give this Lisa Smith to the hash function, Lisa Smith, and it generates an address. In this case, it generates 1, and at that one location, which is a physical, it leads to the physical address, the physical record for 1, which is a key value pairs, which is the record, is stored. So this is how hashing works. So the trick is, without using any BST, you can straight away go to that index and get to the physical record. Whereas in BST also you have to do this log n. This will take log n units of time. This is here, the amount of time taken is whatever the amount of computation time HF uses, hashing function uses to take John Smith and generate 873, or take Lisa Smith and generate 1, or take Sam Doe and generate 9898. That is the job of the hashing function, to generate this 998s or 872s or 1s, which will directly lead to the physical addresses. So that's what is the promise of hashing. Okay, so this is the central idea behind hashing. So with that, let's proceed to the next slide. Yeah. Okay. Okay. So dictionaries are key value pairs. I think there is get key, delete key, insert key. So dictionary is a classic hash map where you have key on one side and its associated index on the other side. Okay. Next, I don't think we need. So yeah. So this is the slide which I would like you to get it. See, the time complexity for tree methods, whether you're using an AVL balanced tree or a BST, the time complexity is O of log n, or in the worst case O of size. If you're not using any tree organization, or if it's a degenerate tree, remember it could be a BST and it could look like a linked list. We talked about this before when we were discussing the balancing of the tree. We discussed this. So if you have a tree, it can go into O size, or if the tree is well balanced, O log of n. Whereas with hashing, the expected output time is O 1 unit of time. That's it. So it can happen in 1 unit of time itself. Okay. So that is the promise of hashing. So there are two kinds of hashing: static hashing and dynamic hashing. We are going to look at how it happens. So now you should focus on understanding how hashing actually works. Okay, let's move on. Okay, so the key value pairs are stored in a fixed size table called a hash table. A hash table is partitioned into many buckets. Each bucket has many slots, and each slot holds one record. A function hashed f of x transforms the identifier key into an address in the hash table. Okay, so let me elaborate this without this is called static hashing. So let me elaborate what happens. Okay, so I will take a little explanation. So the way this is organized is like this. Okay, and you will have to understand this. Once you understand this part, hashing is by and large understood. So these are the buckets. These are called buckets, or you can call them indexes or whatever. So let's call this bucket 1 or bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, and so on. So now let's say you have to hash on employee number. So employee number comes in. E number is equal to 101, 101. That is applied to that is given as an input to a hash function. So the hash function takes 101 as a parameter and generates an index, let's say B2. Okay. So at B2 index, I will store the record 101. So here I will store the record 101. Okay. Now just listen to it carefully. Now HF comes again. Now I am going to store 103. So what am I going to do? Again HF does 103. Maybe since it's a random function, it generates an address, let's say B4. So HF 103 generates the address B4. So I keep this at B4, record 103. Okay, this record 103, its data is recorded in this bucket B4. Okay, so what is HF giving? It is giving the bucket address or bucket value. Okay, it is identifying which bucket this should go into. But if you see here, there are only 5 buckets. The number of buckets are less often. Okay, less than the amount of data that you have. You cannot have as many buckets because a lot of these buckets will be empty. So you can the storage will go. So what they do is the domain is employee number, but their range is the bucket number. But what happens with the bucket number is the number of buckets. So number of buckets will be much smaller, will be less than the employees, number of employees. Number of employees. Now that is going to pose a problem. And now why do I have it that way? Well, the reason I have it that way is because I cannot waste so much space on buckets. Buckets are only what are needed. Okay. So the buckets will be only these many. Now what is the problem? The problem is called collision. So what may happen is HF 205, okay, may also generate an address which is bucket 2. Okay. Now why does that happen? Because it's a randomization function. Though there may be no connection between 205 and 101, both may map onto the same bucket because your hashing function has produced this bucket, and for 205 also it has produced the same bucket. So this is called a collision. This is called a collision. Collision has occurred at which bucket? At bucket 2. Why did the collision occur? Because the hashing function was not very good. Hash function of 101 and hash of 205 both collided into the same bucket B2. So all the data for 205 and 101 went into the same bucket B2. Now the bucket, how can it hold more data? So for that, every bucket can have slots. So now that 205 has also collided into the same bucket, the bucket expands, B2 expands. Now there is a linked list kind of thing maintained at every bucket level. So now you have 205 in this bucket. Okay. So this is because collision happened. So the more collisions happen at B2, the number of slots, these are called slots. This is slot 1, slot 2. The number of slots at that bucket will go on increasing as more and more people collide in B2. But a similar thing may happen with B3, B0, B1 and B4. Now, if the collisions have to be less, as much less, then the hashing function should be good. It should be a very, very randomizing function, so that it spreads out data and doesn't allow two or more unrelated records to collide and then create this. Now you will ask, why is this creating of or expanding buckets into slots a bad thing to do? Okay, why is it a bad thing to do is very simple. Now look from the other side of the story. Let's say you're looking for 205. That is, this is for entry of 205. It is stored here. In this way, in this bucket it is stored. Now I am looking for 205. When I am looking for 205, what will happen? In the same way like what we did while inserting, if you are looking for 205, you will again go to the hash function HF and give 205. Again, the good part of this hashing function is, if the same input is given, the hashing function will generate the same output. That is guaranteed. That is one of the qualities of the hashing function. Given input, it generates the same output. For if two inputs are same, the output is same. So it's a 1-1 function, 1-1 and onto function. Okay. So, well, it's not really onto, but it's a 1-1 function. So HF of 205 will always also generate B2. Okay. Now, remember now I am looking for 205. Now I have landed upon this bucket. Now this one was fast. This took 1 units of time. But the danger now is, though reaching the bucket took only 1 units of time because it was only a computation. Now what happens? Now I have to follow a linked list at that bucket, which is the slots. I have to follow a linked list. Now this linked list will take units of time, n units of time, depending on how many records have collided in this bucket. If there has been a lot of collision, this n will be very big. If there are not collisions too many and the data is more spread out, then you have a good n. So you have to understand this, that the n depends on the quality of the hashing function, or n, which is this number of slots in this bucket, depends on how many people collided into this bucket. So it also depends on the quality of the hashing function and also the amount of data you have available, amount of buckets available. Obviously, if you have more buckets available, this is better. Okay. So this is called buckets, and these are called slots. So after a record has hit a bucket, then it becomes a linear search, and that is where situation starts becoming worse. Of course, a lot of people have debated whether it should become a linear search, or can you maintain a BST here in combination with this. So a lot of things have been done, and we will study a few slides to understand this. What are the different ways of this? Is called static hashing, because everything is static here. There is no dynamic thing. I will come to dynamic hashing in a moment, and we can appreciate that. Okay, so if this is clear, we'll proceed and try and understand how this thing looks like. So let's go forward and see how this looks. A picture. So this is the, as you can see in this picture, these are the buckets. These are the buckets. Okay, and these are the slots in a bucket. Now the slots are connected using a linked list, which I showed you. Okay, so these are the slots, because here the search becomes linear. Okay, now you could implement it as an array slot or something, but this becomes a linear search. Okay, whereas this was very fast. You reach the bucket in 1 units of time. After that, things get slowed down because you are going through a linear search. These are the slots. So if you are okay with this, we will proceed to the next part. Okay, we will move on. Yeah, we'll rub off. Easier to rub. Okay, now let's move on into the next thing. I don't think it's important to understand the data structure here. Okay. Now these are some other uses of hashing which is done, which is not relevant at this stage. Let's move on. Yeah, it's a 1-1 onto function. I'm not sure whether it's onto or not. Obviously it's not, but it's 1-1. Okay, next. I don't think this slide talks too much either. Next. So yeah, so this probably you should look at it for a moment, and I'll wait for a few moments for you to assimilate this slide, and then we'll move on. Please try and assimilate this slide. There is nothing in it which I have not discussed. So we have an array which is the array of buckets. Each position in the bucket. So if you will, this looks like this. Okay, we have a array of buckets. This bucket B1, B2, or B0 to B-1. This is the bucket. A hash function converts each key k into an index in the range 0 to B-1. So these are the buckets. It has to go to buckets. Every dictionary pair key element is stored in its home bucket, which you obtain from this. So using this, suppose you want to store key 101 and element is the employee record. Where will it be stored? In the table. In which bucket of the table? That bucket of the table is generated using f of key. What is f? F is the hashing function. This is what I was saying. So f, you take the key, that is 101, let's say, apply the hashing function to it. You get some bucket ID, let's say bucket 2. So in table, you go to the second bucket in table 2, and in that bucket there may be, when collision occur, there will be more slots. Okay. So let's move on. Okay. Now there is a small mistake here. Okay. Anybody? Okay, I'll wait for a couple of minutes. There is a mistake on the hash function. Anybody caught it? Switch to mini control. Small mistake. No. Are you guys there or 3D 33C, no. Again I will show you. There is a small mistake on the hash function. No one? I will show you again. Okay. The mistake is this: the hash function is key mod 11. Is it really key mod 11 in order to yield this? It looks like it's key divided by 11. Because if you see 22A, in which bucket is it getting stored? It is getting stored in bucket 2. How did you get bucket 2? You divided 22 by 2 and you got this data has to go to bucket 2. So this data went to bucket 2, right? Then 33C divided by 11. Key is, this is key, this is value. So you are storing that whole thing at that particular location. This could be big, okay? This record could be big, but this is the key on which you are storing. And remember there are 8 slots. So key mod 11, it goes into the 3rd slot. Then 3D, 11 by 3 is 0, so it goes into the 0th slot. 73 by 11 is 6, so it goes into the 6th slot. And 85 by 11 is 7, so it goes into the 7th slot. So this is how the data is stored. Okay, here there are no collisions. So the data is stored in this manner. So these are the buckets. So this is bucket 0, bucket 1, bucket 2, and so on up to bucket 7. 8 buckets are there. 8 buckets are there. This is how the data is stored. Okay. So moving on. Okay. Now we'll talk about collisions. Okay. So this is the original data. Now a new piece of data came in, which was 26G. Okay. So now what happens with 26G? So using the same logic, 26 divided by 11 is 4. Actually at 4 there is nothing. No, 26 divided modulo of that is divided is 2. Sorry. 26 by 11 is 2. So now you have a collision. Why you have a collision? Because 26G and 22A have both go to the same slot. Okay, it's by 11. So they have to go to the same slot. The hash function is doing key by 11. So they have to go to the same slot. So these are called synonyms. Now this is called a collision. This is a bucket. In that bucket there is collision. Now what do you have to do? In this element of the bucket you have to developing a linked list where 22A is first, 26G is the second. Okay. So because this bucket is already occupied, this is called a collision. Okay. A collision is occurred. So now in this bucket a linked list has to be developed, which will slow down the operation. Okay. The performance is bad because maybe A, our hashing function is not good, or B, the amount of data we have itself is less. I mean the total number of buckets itself is less. Both can be the reason why we are having collisions. Okay, but we have to understand what is collision. And the elements which are colliding are called synonyms. This is a nomenclature which is used in hashing. These are called synonyms because they are trying to occupy the same bucket. Why are they trying to occupy the same bucket? Because the key by 11 is the hashing function we are using to go from the index to the bucket. So both will land up in the same bucket. Okay. Okay. So going forward, so this is called a collision. Now you can resolve the collision by creating slots in that bucket or synonyms for slots for synonyms. Okay. So we will erase the screen and then move on. Okay. So Yeah, I will leave you to understand this. What does this mean? So hashing function choice is always a tricky story. If you have to avoid collision, then your hash function should be good so that it randomizes. But I mean, there is going to be a collision, however good your hashing function is, if the amount of or the size of your hash table is limited. That is called overflow, and that is a way to handle a collision. So overflow is a strategy to handle collision. Okay. So what do you do? Now here you are having a situation where there are 24 slots. Okay. Sorry, 26 slots, and you are going by the starting letter. Your key function, hash function, is saying if you are starting with A, you will go into a 0 bucket. If you are starting with B, you will go into 1 bucket. Like that. That is your hashing function. Not a good hashing function, but that is what it is. So what is happening, as you can see in the picture, char and seal both have the same starting letter. So both are going into the same bucket. Okay, they are synonyms. So they are going into the same bucket. At that bucket, so this is the bucket. Sorry, this is the bucket. So at that bucket there is a collision between, this is char and core, seal will collide here. Sorry, he is doing base 0. So it will collide in bucket 2. So it is doing base 0. So char and seal will collide here. So it will occupy slot 0 and slot 1. And there will be a link list kind of thing at this bucket for accommodating these two. Because you cannot accommodate, there will be only one slot available, and you cannot accommodate both char and seal in the same thing. So you will have to form a linked list, and that will deteriorate the performance. Okay. Similarly, if you have clock and C time, that will also collide here. Clock and C time will also, because you are going by the first character, so that will also collide, and you will have this. So this is another kind of hashing. Not another kind of, it's static hashing. This is just an example. Okay, we move forward. Okay, so choice of a hash function, what should it be? It's obvious. What should it be? No, go back. It should be easy to compute so that it's fast, and it should not generate bucket addresses such that there are too many collisions. So it should try to reduce the collisions. So if a hashing function groups key values together, which is bad, this is called clustering. This is bad for bad hashing. Okay. A good hashing function uniformly distributes the key values uniformly throughout the range. So it doesn't, a bad hashing function, there are 3-4 keys, all of them come to the same, this is bad hashing function. They all end up in the same bucket. This hashing function is bad. A good hashing function, what it will do? If many requests come to that hashing function, instead of generating collision, okay, let me draw a good hashing function. How should it look? So if I have multiple values coming in, if it is a good hashing function, and this is my hash table where buckets are there, so ideally it will map this guy to this bucket. Okay, it will map 2 to this bucket. It will map 3 to this bucket, 4 to this bucket. This is a very good hashing function. Okay, because it has distributed the keys across the hashing table. This is a good hashing. But you are always not lucky to get such nice hashing functions. Okay, next. Okay, so moving on, they have given some examples of hashing function. I think we can skip this. We'll move on. Okay, these are some more hashing functions. We'll still move on. There's some more hashing strategy, hashing by division, whatever. No, not important. These are just different kinds of hashing. Either you do division or you do modulo. Okay, next. Next. There are other kinds of hashing functions, some generating. Next. I think we will not spend too much time here. Overflow handling. Okay. Now, now we are going to talk about something, and then we are going to end this discussion. So, yeah. Now we are going to we have looked at what is called static hashing. Now, in static hashing, what happens? In static hashing, the hash function generates the address of a bucket. Now, if in a bucket if collision is there, then basically at that bucket a linked list is formed, or we call it slots are formed. And that degenerates the performance. Why? And what is the way out? You should have large number of buckets so that you can distribute better, and you should have a good hashing function which is capable of distributing data across the buckets. Okay, not focus them all in one buckets. Okay. Now you need to know that for your exam and for general knowledge, and you also need to know some things like what is linear probing and what is quadratic probing. Both come under the general topic of open addressing, also used in dynamic addressing. Okay, dynamic hashing. So I will look at a few examples of this, and we'll end our discussion on hashing with that. So I'm going to show you what is linear probing. I'll show it with example. That's better. Okay. Okay. So my hashing function, which I'm involving right now, is divide whatever number is given to you to get the bucket. Do a modulo 17. So if you give me 101, I'll do modulo 17 to decide which bucket I am going to put this data. Put 101 in. This is my hashing function, modulo 17, and pick up the remainder. Whatever modulo 17 gives, that gives me the bucket number. That is a very trivial hashing function. So let's see what happens, and in that context, let's see what is linear probing. And once you understand linear probing, you will understand quadratic probing also. Okay, let's move on. Okay, home bucket. This is what I just said. Home bucket is key modulo 17. Okay. Okay, now you have 0 to 16 elements, because the bucket size is, the number of buckets are 17 and you are using modulo. Now let's go on inserting data and see what happens. Okay, let's just watch it. So insert pairs whose keys are 6, 12, insert data whose keys are 6, 12, 34, 29, 28, 11 and so on. Okay, so let's do it very quickly and you will understand how it happens. So just watch very carefully. So 6 modulo 17 is 6. Okay. So what will happen? This will go and sit in the slot number 6. Where is slot number 6? 0, 1, 2, 3, 4, 5, 6. So 6 will come and sit here. Okay. The value here will come and sit in bucket number 6, not slot. Bucket 6. Okay. Then I have 12. 12 modulo 17 is 12. 12 modulo 17 is 12. So this will also come and sit here. So the 12 will come and sit here because I have the slot empty. Okay. Now 34, that's the third value. 34 modulo 17 is 0. Okay. So this 34 value will come and sit in bucket 0. Okay. This will sit in this bucket. 34 will sit in this bucket. Then 29, where will 29 come and sit? 29 is modulo 17. We are always doing modulo 17. 29 modulo 17 is 12. Okay. Now it goes here. It finds 12 is empty. Now, if it was using static hashing or our old thing, it would have formed a queue. So it would have formed something like this to store what was the value? 29.
29.
It would have stored 29 here. This is what would have happened in static hashing. right? This would be the bucket, and in that bucket it would form slots. But this is what static hashing would do. But what does linear probing do? It says, okay, the slot that you wanted to occupy, or your designated slot, the bucket you wanted to occupy is 12, but it is occupied, so just take the next one. It just says take the next one. So in this case 29 will come and sit here. Okay, so this is how it will look, because that is what is linear probing. It is not going to create an auxiliary linked list and store. It is going to see the difference. In static hashing, I will create a linked list. In dynamic hashing or in linear probing, I will try to store the overflow. The overflow here will go into a separate slots which will form in this bucket. Here it will be accommodated in the same array where the data is. At which position, which slot in the, which bucket in the array? The next available bucket after 12, which is free. So if this happens to be free, so 29 will go here. Okay, very stupid, but that's how it is. Now 28. 28 modulo 17 is 11. Okay, so 11 is free, so 28 can come and sit here. 11 slot, 11 bucket is free, so it will come and sit here. Then we get 23. Okay, 23 modulo 17 is 6. Okay, 23 modulo 17 is 6. 6 is again occupied. Now, had it been static addressing, it would have formed a slot here and a list here, and it would have accommodated there. But since we are discussing linear probing, it will look at the next available position after where it was designated to go. It was designated to go here, so it will go here. Okay, so this is what will happen. 7 modulo 17 is 7. Now what has happened is, you see something peculiar. 7, now I am trying to insert 7. 7 modulo 17 is 7 only. So it should have come in the 7 slot, which is here. Okay, this is the 7 bucket. It should have come here, but it can't come there. Instead, because it's already occupied, instead it has to go linear probing. It has to go to the next location. Okay, that is 7. 0 again. 0 modulo 17 is 0, so it should have come here. But since this is full, 0 has to come here. Okay. Then 33 modulo 17 is 16. 16 is empty, so 33 will come here. Okay. 30 modulo 17 is 13. Unfortunately, 13 is filled, so it takes the next available slot and puts 30 there, right? Yes, sir. Then we have 45. 45 modulo 17 is 11. 34 and then 11. Now 11 is already here. 11 should have come here, but this is already occupied. After that, all are occupied. So 45 will come and sit here. It starts from here and goes forward. Okay. So now, let's see what happens when I am looking for 30. Okay, I am looking for 30. This is how the tree will be. This is how the array will be filled in linear probing. Now let's say I am looking for 30. If I am looking for 30, what will happen? I will do the same hash function. So 30 modulo 17, which will give me 30. So I will go to location 13, which is this. Okay, I find at 13 it's not there. I have some other value, but I know this may be to handle overflow. So I look at the next value and next value, because I am doing linear probing. I know linear probing has been used to store. So if I don't find it here, I look at the next. I will find it here. So this will slow it down. Remember, this now becomes a linear retrieval. So this will slow it down. I went to 29 very fast, but that was occupied. After that, I have to proceed linearly. Okay, so it will slow it down. So does everyone get how we stored data? I'll pause here for a moment and ask this question. Did you understand what linear probing means? I did not allocate 11. Okay, I think I did.
missed.
Okay, we'll go back. 11, you know where it will come. Oh, I skipped 11 in between, is it? Oh, okay. 11 should come here, but if this slot is over, then I will allocate 11 after that. I think I missed the earlier thing, got cleaned out. Huh?
Yes, sir. Sorry.
Because I did not store it. Okay, I think we have a picture in this slide itself. We have a picture. So you will see how 11 gets stored. Go next.
6, sir.
See, he's filling it up. Watch. There's an animation going on. So 29, 28, now 11 comes. See, 11 went there. Okay. Then 23 came here. 7, 0, 33, 30, 45. 45 went there. Because, okay, because we did not fill up 11. Oh, sorry, you are right. Because we did not fill up 11, this slot we did not fill up. In our picture we had 45 here, I remember.
Yes.
Okay, because we did not fill up 11. If we had filled up 11, this would have been occupied, and 45, which actually should come to 11, 11 is here. It will go on searching from there, and it will find the first free location, it will get it here. Okay. That is what would happen. Okay. So, okay, so this is what is the problem. So once the linear probing, okay, now there is something called linear probing and there is something called quadratic probing. Now you'll understand the difference easily using a picture rather than on the slide. Okay, what is linear probing? If there is a, just watch what linear probing does. Remember, these are all dynamic hashing. So if linear probing, you get here, and if this slot is full, you go to the next one. Okay. So, and if this is full, you go to the next one. And then when it is coming back, you go here. Now, what is the disadvantage of linear probing? Okay. What they say is data tends to cluster. That is, you have guchas of areas near this clustering. Because it is doing linear probing, it is looking at the next location, next location. Suppose this bucket is very popular, all the subsequent guys will be occupied, which are mapped to this. That is what will happen in linear probing. Among the data, clusters will form. Like if you visualize what will happen in linear probing is that at particular points there will be clusters forming. There will be values at various points. These are values where they have come, and because they are full, we have filled the next subsequent values. Okay, so this is what linear probing results in. This clustering of data in the hash table. This is the hash table, the big one where you are mapping. So there is danger of clustering. So instead of that, they use what is called quadratic probing. So when you map to a location in quadratic probing and it is filled, so let's say you map to a location L, the next location in linear probing, you map to a location L and let's say L is filled, then where do you look? You look for L plus X, that is the next value at index L plus X. In quadratic, you don't look for L plus X, instead you look for L plus X squared. So when your first time X is 1, these are same. So if your collision happened at in linear probing, the locations which will be filled up are L, L plus 1, L plus 2, L plus 3 because of linear probing, one after another. If everything get mapped to L, the way they are going is like this. Whereas here it will be L, L plus 1, L plus 4, L plus 9 and L plus 16. This is how it will go. So what will happen is the values, if you see with this, the difference between quadratic probing and linear probing, the values here will be more distributed. Even though they are colliding at L, they will be more distributed across. They will be distributed across the hash table when you use quadratic probing. So that is called quadratic probing. Okay. I hope the distance under meaning is clear. The difference is clear between linear probing and quadratic probing. The difference between linear probing and quadratic probing. Okay. Then there is another thing called double hashing or rehashing. What do you do? If you have a collision, use another hash function to generate the value. Okay, so you use the first hash function. If there is no collision, keep it there. If there is collision, instead of using this function x squared, use another hash function on the value to generate it the next address. So the jump address, the address with which it should jump, like +1 or something, will be generated by the hash function. So L plus hash of that value will be where you will go. So this is called double hashing. Okay. So as far as your basic knowledge goes, you should know what is hashing. You should know what is the static hashing, where collisions happen, buckets linked list are formed. Then you should know what is open addressing or dynamic hashing. We should understand what is linear probing, what is quadratic probing, what is the difference between quadratic and linear, what is the advantage of quadratic over linear. The data is more distributed, they don't form clusters. Then what is double hashing? If you are clear about these some basic things, that's all you need for understanding hashing and for writing a paper. Okay. So is this part clear for you guys? I am asking a question. Are you clear? What is the basics of what is hashing? What is the old style hashing? Then what is the dynamic hashing, which is linear probing, quadratic probing? If you're clear about that, that is all we are interested in getting to you as far as hashing is concerned. So can we move forward to some Python type, Python code? Flask, is it ready? Oh, it's ready? Okay, so what we will do is we'll take a pause for 5 minutes to switch to Python so that you also mentally switch from hashing to Python. We'll give you a 5-minute break in between, and then we will do it for another half an hour. We'll do a bit of Python to help you understand, how Flask works. Okay, so let's do that. Okay, so that. Okay. Now we are slowly inching forward in our course of data structures. The next topics that we will do are interesting. They are to do with graphs. No?
Yes.
So they will do the graphs. Okay.
String pattern matching.
First graphs, no? So you have basically 2 topics left: graphs and pattern matching, and sorting and searching. I think sorting and searching I am not going to do. Either you are going to do it on your own, or will ask someone else to do it. Okay, I am not going to waste my time. There is a very little conceptual thing there, so you can figure it out on your own. Okay, but apart from that, we have graphs and we have trees.